Hello everyone, thanks for coming. And today we are going to do a brief introduction of our week 7 mathematical induction. So what is a mathematical induction? The principle of mathematical induction is that A be a set of natural numbers if 0 is in A, and for all k natural numbers, if k in A, then k plus 1 is in A, then k is the whole set of the natural numbers. So this is the principle. How to prove this? We can prove this by using the smallest counterexample. So this is often used to prove some propositions that involve the natural numbers. For instance, if k satisfies a proposition, then we show k plus 1 satisfies the proposition, and eventually we show that every natural number satisfies this proposition. So here is a proof template for mathematical induction. So the base case is consider n equals to c, show that PC is true. So this is to show that the smallest case is true. C here can be any integer, not necessarily 0. So inductive hypothesis is to consider n equals to k for an arbitrary integer k where k is greater or equal to c. Assume pk is true, then the next step is to prove that when n equals to k plus 1, the hypothesis is true. Finally, we can conclude that by the principle of mathematical induction, Pn is true for all integers, and such that n is greater or equal to c. So here are some special notes. Actually, we don't need to start from n equals to 0. We can start from c, as we just explained. C can be both positive, 0, or negative. So this technique only applies to natural numbers, not necessarily natural numbers, but it must be the set where we can list from smallest to largest. It cannot apply to like the real or real numbers or positive real numbers because the set has to be countable. We need some special techniques to apply to the whole integer sets. For instance, we can assume that the hypothesis holds true when the absolute value is equals to k, and then we prove the hypothesis is also true when the absolute value of that is the same as k plus 1. So by taking the absolute value technique, we can extend the mathematical induction to the set of integers, but we cannot extend it to the real numbers. So here is another version, the strong induction. So strong induction states that let A be a set of natural numbers if 0 is in A, and for all k natural numbers, if from 0 to k those numbers are all in A, then k plus 1 is in A. If those two conditions hold, then we can conclude that A is a whole set of natural numbers. We can also prove this by using the technique of the smallest counterexample. So here is a template for applying the strong induction to prove a proposition. So the basic case is consider n equals to c plus 1 to c plus d, where d is a non-negative integer. We show that pc to pc plus d are all true. The inductive hypothesis is to consider an arbitrary integer where k is greater or equal to c plus d. Assume that Pn is true for all n such that n is greater or equal than c, but smaller or equal than this k. The next step is to consider n equals to k plus 1. We need to show that k plus 1 is true given the fact that Pn is true for all n, where n is smaller or equal than k but greater or equal than c. Finally, if we can prove the inductive step, we can conclude by strong induction Pn is true for all integers n such that n is greater or equal to c. Thanks for coming.